Today we're going to be talking about velocity and other rates of change. So the instantaneous rate of change is our derivative. So that's how we defined our derivative. Remember, I want you to know that derivative, that definition. So when we say rate of change, we mean instantaneous rate of change. So find the rate of change of area with respect to the radius. So I'm looking for dA dr. So that's our derivative. Now I'm evaluating the rate of change when r equals 4. So all I have to do is plug in 4 and I get 8 pi. Now if r is measured in inches and a is measured in square inches, what's our appropriate units for dA dr? Well, the units on a are square inches over the radius, which is also inches. Now our application having to do with velocity. So the instantaneous velocity is the derivative of position. So the derivative of position is our velocity function. And speed is the absolute value of velocity. So our speed is the absolute value of the derivative of position. Acceleration. Acceleration is the derivative of velocity. Okay, so I look at them like a ranking. You have position. You have the derivative of position, that gets you velocity. When you look at the second derivative of position, which is the first derivative of velocity, that gets us acceleration. Okay, in this accompanying figure, we are given our velocity function. So this is v of t. Okay, particle moving forward. So that's when your velocity is greater than 0. So our velocity is greater than 0 from 0 to 3 and from 5 to 8. Now notice how I included the endpoint, but I didn't include any other points where at 5 or 8 or 3, because that's when your velocity is equal to 0. So you're neither moving forward nor backward. So backward is when your velocity is less than 0. So our velocity is less than 0 from 3 to 5. And that's it. Speeding up. Remember, that's the absolute value of velocity. So when that graph is increasing. So remember, the absolute value of velocity, let me draw that in. Would look something like that. So I need to know when this graph is increasing. Well, I'm increasing from 0 to 1, from 3 to 4, and from 5 to 6. And just so you guys know, all these are in interval notation. Slowing down is when the absolute value of velocity is decreasing. So that is from 2 to 3, from 4 to 5, and from 6 to 8. So same graph, just a bunch more questions with this. Particles acceleration positive. Okay, so that's when the derivative when that velocity is increasing. So I'm increasing acceleration being positive from 0 to 1, and then from 4 to 6. Negative 2 to 4, because our velocity is decreasing, and from 6 to 8. 0 from 1 to 2, I have a straight horizontal line. My slope of my line there is 0. And from 8 to 10, now hopefully I'm going to remember that 10 is an endpoint, so I include that point. In this part, we are asking, when does the particle move at its greatest speed? Remember, speed is the absolute value of velocity. So I'm going to draw in my speed curve. Basically, all of the y's of our velocity curve that are negative are going to become positive, reflecting essentially across the x-axis. So in red there we have our speed curve. When does the particle move at its greatest speed? Well, the highest value is here at 4, and that is from 1 to 2. That is at 4 and at 6. Okay, same one, particle standing still. That means when velocity equals 0. So my velocity equals 0 from 8 to 10.
In this example, particle moves along a line, so that's position for any time t greater than 0 is given by this position function, where s is measured in meters and t is measured in seconds, so that means make sure you give me units. Find the displacement of the particle during the first 3 seconds. So that's just s of 3 minus s of 0. So we have to find s of 3, which is negative 1, s of 0, which is 8. So negative 1 minus 8, and it is negative 9 meters.
Now this part of the example, we're asked to find the average velocity of the particle during the first 5 seconds. So average velocity is the slope through the line s of 5 minus s of 0 over 5 minus 0. So s of 5 in this case is 3, s of 0 is 8 over 5. That simplifies to negative 1 meters per second. Instantaneous means derivative. So our velocity function, which is the derivative of our position function, is equal to 2t minus 6. So then I find v of 5, and that simplifies to be 4 meters per second. Okay, particle moving along the line. S is measured in... Okay, so same piece. I don't know why I was rereading that. Find the acceleration. So acceleration is my derivative of velocity. Remember from the previous slide, our derivative of our velocity was 2t plus 6. So the derivative of that is just equal to 2. Since I have nowhere to plug in a t value, my acceleration is just 2, and it's meters per second squared. Describe the motion of the particle. At what times does the particle change directions? Okay, so particle changes directions when your velocity equals 0. So my velocity equaling 0, I did that wrong. It's minus 6. You know, I did this when I was doing the answers too. Minus 6. This should be a minus up there too. I don't know why I did that. I did that when I was working through the solutions. So at t equals 3 seconds. So describing the motion of the particle. Okay, what's my initial position? The particle starts an initial position at 8 meters. From the interval of 0 to 3, the particle is moving left. Because velocity is less than 0. At t equals 3, the particle changes directions. Change is directions. And moves right when, and moves right for t greater than 3 because v of t is greater than 0. Okay, that's all I have for you today. Please make sure that you fill in the Google form that is right below this video.